Hey everyone, this is lesson 3 in bonding. I'm actually splitting this lesson into 2 separate videos because it went a little long. I recorded the whole thing and realized it was too much. So the first part of this is going to be reviewing how to draw simple Lewis dot structures of molecules, and the second video will be on bond energy. So this is going to take a couple of days of material to get through. So we'll do both videos on one day, and then you're going to have time to practice Lewis structures and practice bond energy the next day. So just consult the schedule. So first of all, when we're talking about a Lewis structure of a molecule, we're dealing with covalent substances. All right, so these are only non-metal Lewis structures that we're working with, and we call this a localized electron model. So when I was going over metallic bonding, so here's a bunch of metal atoms where the nucleus and the non-valence electrons line up, and then the valence electrons form that sea of mobile electrons where they just kind of float across the surface and they're not associated with any one particular atom. We called that delocalized. So when we look at Lewis structures of covalently bonded molecules, we're going to say these are localized, meaning the electrons are staying put. They're just going to be located in between the atoms that we're talking about. So localized electron model, electron pairs are assumed to be localized on a particular atom or in the space between two atoms. So there's two different types of electrons in these Lewis structures. There's lone pairs, which are electrons that are not involved in bonds. They're just kind of hanging out around a particular atom. And then there's the bonded pairs, the ones that are involved in a bond between two atoms. So we have to make sure we account for all of the valence electrons when we're making these Lewis structures. There are 3 different things that this localized electron model can be used for. One of them is Lewis structures, which is the basic idea of how to put these molecules together. The next is predicting geometry of the molecules, which we will talk about in a later lesson. So I'm not really concerned about shapes all that much right now. I mean, we'll get some basic shapes down in this lesson, but we'll talk about more complex ones later. And then also this idea of what kind of orbitals are involved in this hybrid idea that we'll deal with later in the lesson too. So a Lewis structure shows how valence electrons, just the valence electrons of all these elements, are arranged among atoms in a molecule. And it hinges around the fact of this like octet rule that we want to stabilize elements and get them into a noble gas electron configuration. Hydrogen is not going to obviously form an octet. Hydrogen only has one PEL. It can only hold 2 electrons. So hydrogen will make one bond. That's it. It will have one bonded pair. It will have no electrons like hanging around on the outside of it. Nothing. So once hydrogen makes a bond, it's done. Most other elements will form an octet. Most. There are exceptions to that. We can be under. We can be over. We'll talk about those in a later lesson. But we call this like octet rule because noble gases have a completed octet of valence electrons. They have the s block and the p block filled. When you're making bonds, a single covalent bond is going to be represented by one line, which represents a pair of electrons. So just be careful with wording of questions here. 1 pair equals 2 total. So I usually just use a line. It's a lot easier to show than putting all the dots in between. A double covalent bond will have 2 pairs of electrons, so that's a double, that's a double. There should also be lone pairs here, but we'll talk about that another time. And then a triple bond will have 3 pairs or 6 total electrons. So this is probably the most important slide of this whole lesson that goes through the procedure. It's very systematic how you can go about drawing and making these Lewis structures for molecules. If you follow this procedure, it's going to be extremely useful to you in drawing simple molecules as well as more complicated ones. So it's just a few steps to remember, and it gets very routine once you learn how to do it. So the example that we're doing here is for carbon tetrachloride, CCl4. Now you might be like, oh, that looks like CH4. I know how to draw CH4. It's going to look exactly the same, but as we kind of branch off into other types of molecules, this method will be very helpful for you. So the first step is to count up how many valence electrons are going to be present in the entire molecule. Since we're dealing with nonmetals here, we're primarily dealing with hydrogen and then groups 13 through 17. Okay, so you deal with 3, 4, 5, 6, 7 valence electrons based on the group number that it's in. So for carbon tetrachloride, carbon has 4 valence electrons. It's in group 14. And chlorine's a halogen, group 17, so they each have 7 valence electrons, and there's 4 of them. So there's 28 valence electrons for the chlorines, plus the 4 valence electrons from the one carbon, which means I have this total of 32 valence electrons. What that means is when I'm done drawing my Lewis structure of this molecule, I must show either with bonds or lone pairs a total of 32 electrons. If I don't, then I'm wrong. First thing we're going to do is set up like a skeleton model of this molecule. And again, based on the pattern of this formula, you should recognize that this is going to be a tetrahedron shape. You're going to put, basically the element that's a single is going to be your center element, and then you'll arrange the other ones around the perimeter of it. Really what you're going to be doing is put the least electronegative element in the center, as long as it's not hydrogen, because hydrogen can't have anything branching off of it. You can only have one bond, so you can't like arrange hydrogen in the center and have multiple things coming off of it. How do I know that carbon's the least electronegative when I don't have the electronegativity numbers? Electronegativity increases from left to right. So since carbon's group 14 on the left and chlorine is group 17, which is further to the right, chlorine's electronegativity values would be higher. So carbon goes in the center. And then since I have 4 chlorines, I'm just going to arrange them symmetrically around that center carbon. So then what you're going to do is you're going to connect those peripheral atoms to the center atom, starting with 1 bond apiece. And what you're going to do there is count, well, how many electrons did I just put into my drawing, and subtract that from the total that we need to hit. So since each bond counts for 2 electrons, those 4 blue lines that I just drew is a total of 8 electrons that I've put into my picture. I subtract that from the total of 32 that I need, which means that my picture is still lacking 24 electrons. The next step, so we just did step 1, step 2, step 3. What's that shape thing just happened? Now step 4, you look at your peripheral atoms and you complete their octets. So since these chlorines here, that bond counts as 2, each chlorine still needs 6 more electrons to complete its octet. So by putting these 3 lone pairs on each chlorine, 3 lone pairs is 6 total electrons times 4 chlorines gives me 24, which means that my molecule is complete now. I've run out of electrons. I have 32 electrons in my picture. Everybody's octet is satisfied. If I had electrons left over and the center atom did not have a completed octet yet, then any remaining electrons would go on to that center atom. You'll see examples of that in a later lesson. Double check your work. Make sure that every atom has 8 valence electrons only. So look at, here's chlorine, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And then this carbon in the middle has 4 bonded pairs for a total of 8. It has no other lone pairs present. When you're making a Lewis structure, so let's look at this HCN and go through our procedure. Hydrogen has 1 valence electron, carbon has 4, nitrogen has 5. So my picture needs to have 10 electrons. So I put carbon in the center. I start by connecting carbon to the peripheral atoms with bonds. So that's a total of 4 electrons, so I had 6 left. So I put those 6 electrons around my peripheral nitrogen atom. I can't put anything around hydrogen because hydrogen's done, but I completed the octet for nitrogen. So I put 10 electrons in my picture, but carbon's octet is not satisfied and there's no electrons left. I can't just do this. I can't put in extra electrons. It doesn't work that way. So if you've run out of electrons in your picture and your center atom doesn't have a completed octet yet, swing some of those lone pairs over and turn them into bonded pairs. So if I only swing 1 pair of those electrons over, and I do this, here's 2, 4, 6, 8, 10. I didn't draw any more electrons in. The nitrogen has a satisfied octet, but the carbon still only has 6. So if I swing this other lone pair in between and make it into a triple bond, well, now hydrogen is satisfied because it can only have the 2. Carbon is satisfied, 2, 4, 6, 8, and the nitrogen is as well, 2, 4, 6, 8. Okay, it's going to take, you have to practice these, but they really aren't going to be super complicated. The basic geometries that we'll start out with here are linear molecules, bent, pyramidal, and tetrahedral. We'll talk about like how you can predict whether a molecule is going to be linear or bent, or, you know, is it going to be a trigonal pyramid or plane? There's a lot of different shapes involved. There's a PhET simulation on molecular shapes that you'll be working on later in this unit that's excellent. Like, I highly recommend really studying that PhET simulation. It would go along with a little lab that you're going to do. You know, if we had molecule kits, this would, you know, you'd see it in 3D, but the PhET simulation's awesome for figuring out molecular geometry. So we'll talk about, you know, what makes a molecule a certain shape. But these are 4 that you had to learn in Regents chemistry. You know, there's some molecules that you should just memorize. Like if you obviously have a diatomic, the only option you have is to put it in a straight line. Carbon dioxide is a straight line. You need to know that water molecules are bent. We'll talk about the actual angles involved in some of these bonds too. When you draw these molecules, if you find that you have an asymmetrical structure to it, you'd call that a polar molecule. And if you have a symmetrical structure to it, it's nonpolar. So this is the SNAP mnemonic device that you used in Regents chemistry. So symmetrical molecules are nonpolar, asymmetrical molecules are polar. Why this is important is because depending on the polarity of the molecule, you get different intermolecular forces involved, which is like our final little unit that we have to talk about. It also has to do with the way that the molecules will interact with each other. Polar molecules will interact well with other polar molecules and form intermolecular forces with them. Nonpolars will interact with nonpolars. So I'm going to take you through these examples of how to draw some Lewis structures of a bunch of these. And then that would be basically the wrap up for this first lesson. So I'm going to go through methodically how to put these together, you know, counting your valence electrons and such, just to show you the routine. So if I want to put 2 hydrogens together, I have 2 hydrogens, each with 1 valence electron. So my picture needs to have 2. So this is the simplest molecule you'd ever have to draw. You'd never have to draw this in an AP question, obviously. Who knows what AP exam is going to look like this year. So that's a molecule for hydrogen, right? So I have the 2 electrons there. It's done. I don't put any other lone pairs around it. For a water molecule, I want you to remember that water is bent. So we're going to draw it bent right off the bat. Here we're going to put the oxygen in the center because I have 2 hydrogens. They can't have anything branching off of them. So then you connect the oxygen to the 2 hydrogens. So in terms of bond electrons, I have 2 hydrogens times 1 valence electron. I have 1 oxygen with 6 valence electrons. So my picture needs to have a total of 8. So right now, with these 2 lines that I've drawn, that's 4 out of the 8 electrons. I need to draw in 4 more electrons. The hydrogens are done, so the only place where I can put those 4 electrons is on the oxygen, and that completes oxygen's octet. It gives me 8 electrons, and we're good. Next one is ammonia. Nitrogen has 5 valence electrons, and then there are 3 hydrogens with 1 valence electron apiece. So my picture here also needs to have 8 electrons. Again, take the single element and put it in the center, and then branch off the hydrogens around it. So by putting those 3 bonds in, that's 6 electrons, okay? So now I have to put 2 more electrons in. Hydrogen is done, but the nitrogen with these 3 bonds only has 6 electrons showing. It needs an octet. So that extra lone pair goes on the nitrogen. This is a trigonal pyramid shape, and you'll see that more when we get into actual molecular shapes. For oxygen, I have 2 oxygens with 6 valence electrons apiece. So I need to show 12 electrons in my picture. There's only one way to arrange 2 atoms, and it's next to each other. So the first thing I'll do, you can just memorize the bonding for oxygen. I would if I were you, but let me show you the trial and error method. I'll start by connecting each oxygen to each other with a bond. So that's 2 electrons. I have 10 left. Well, I got to complete the octet here and the octet here, but that's 12 more electrons than I put in. So this is 14, and I can't have that. And if I take this away, so I only have 12 electrons, that oxygen on the right no longer has an octet. So instead what I'm going to do is I'm going to take one of these lone pairs and swing it in between the two oxygens. So now I have a double bond, so that's 4 electrons. The oxygen on the left has 4 valence electrons right now, 5, 6, 7, 8. Same thing with the oxygen on the right, there's 4, 5, 6, 7, 8. So I have a total of 12 electrons here, 2, 4, 6, 8, 10, 12. Oxygen has a double bond, I would just memorize that. The carbon tetrafluoride is going to have the same geometry as the carbon tetrachloride that we just made on the prior slide because they're both halogens. So we have 32 electrons that have to be shown here. Just don't forget to put these lone pairs in. If you omit the lone pairs, you're wrong. So make sure you do that. For nitrogen, it has to have 10 electrons in total. Again, this is another one, if you memorize the bonding, it's going to save you time. But if I start out by doing a single bond and then start to complete my octet, I run out of electrons. So I have 10 electrons here, but this nitrogen's octet is not complete. So I have to swing 2 lone pairs in between and make this a triple bond. So here's 2, 4, 6, 8, 10. And then this has 8, this has 8. So nitrogen has a triple bond. For Si2, sulfur has 6 valence electrons, and then 2 iodines with 7 apiece. That's 14 plus 6. My picture needs to have 20 electrons in it. So I have the sulfur, it's on its own, it goes in the center. And I have 2 iodines. So I'll start by connecting them with single bonds. So I've just drawn 4 electrons, right? 2, 4. So I have 16 more to put in. My next step is to complete the octet for my peripheral atoms. So this iodine needs 6, this iodine needs 6. So I just drew 12 electrons in. So I've drawn 16 electrons in total. I need to put in 4 more. Well, that sulfur's octet is not complete. It only has 4. 5, 6, 7, 8. This actually should be bent. And once you learn how to predict that, it'll be easier for you to just draw it right off the bat as bent. It has to do with the number of bonds it has versus the number of lone pairs on that center atom. It would help you to predict the geometry. So this is the same shape as a water molecule. You can see in terms of the bonding pattern and the lone pairs on the center atom, it's the same. The only difference is obviously the iodine has the extra, why isn't that showing up right? The iodine has the extra valence electrons around it. Fluorine, 7 valence electrons and 2 of them. I need to have 14. Fluorine, single bond. Well, now I need to draw in 12 more. 1, 2, 3, 4, 5, 6, completed octet. 1, 2, 3, 4, 5, 6, completed the octet. Nice and simple single bond. Pi3, phosphorus is group 15, so there's 5. And then 3 times 7 is 21, so 26 electrons have to go into this picture. I'll put the phosphorus in the center, put the 3 iodines around it. So I just drew 6 electrons in, right? So I have 20 more that I have to put in my picture. I complete the octet of my peripheral atoms. So I'm putting in 18 electrons right here. I need 2 more electrons. Where are they going to go? Well, phosphorus doesn't have a completed octet yet. Now it does. So this structure, this is going to be a trigonal pyramid. It's going to be the same shape as an ammonia molecule. You can see that the bonding around the, this is annoying, it does that. The bonding around that center phosphorus atom is the same as in the lone pairs is the same as it is on the ammonia. Which again, you'd be able to predict that better in a subsequent lesson. In this last example, the silicon tetrahydride, silicon has 4 valence electrons. Each hydrogen has 1. So I need to have 8 electrons in my picture. And you can kind of predict how this is going to go. The silicon will go in the middle. Hydrogen's around the outside. So that's a total of 8 electrons. The last thing here is when you have a molecular structure and you tell that it's polar, meaning asymmetrical, you can predict the direction of the partial positive or partial negative charge based on electronegativity values. And again, you don't have to know electronegativity values, but you have to know the trends. So when you're dealing with nonpolar or symmetrical molecules, this doesn't apply. The reason why is because there's no net dipole moment. So a dipole moment is when you have a polar molecule. For chlorine, which this should have lone pairs on it, for chlorine, it does not have a dipole moment because it has a nonpolar bond and it is symmetrically arranged. So there's an equal distribution of electrons all around this molecule. Now with methane, CH4, the carbon to hydrogen bonds, these are polar covalent bonds, right? But since each of these polar covalent bonds is identical to all of the others and it's symmetrically arranged around the center atom, all of these little polar areas cancel out and it makes the molecule nonpolar. So there's no dipole moment here. But with hydrogen chloride, it has a polar bond and the molecule is asymmetrically arranged. So we have this polarity to the molecule. The side of the molecule that has the more electronegative element is going to be the more negative side of the molecule. So you might be given a structure and asked to draw in the dipole moment. You would draw an arrow where the arrowhead is facing the more electronegative element. And you can also put like a plus through the back end of the arrow showing where the positive side is. That's absolutely fine. The same thing would happen with this hydrogen sulfide. Sulfur has a higher electronegativity than hydrogen does. So the dipole moment would be the negative region in the sulfur direction. So I hope that gave you a nice little intro to Lewis structures. The biggest thing is counting your electrons and putting those skeleton structures together properly. Don't worry about predicting shapes just yet. You've got to get down how to put the molecules together. The next section of this lesson will just be on calculating bond energies.